Good morning, everybody. This is third day of Argonne 5th quantum computing tutorial. I'm your host, Yuri Alexeev at Argonne National Lab. And today's speaker is Ruslan Shaidulin. Ruslan used to be working at Argonne. He was a director's fellow, but now he's in JP Morgan and Chase. He's a vice president for applied, he's applied research lead. And Ruslan is going to talk about how to solve combinatorial optimization problems using QAOA quantum algorithm. QAOA stands for Quantum Approximate Optimization Algorithm. And Ruslan is truly expert on this in this area of research, and it's a great pleasure for him to give this presentation. The presentation will have following format as before. We'll have for 1 hour Ruslan will give a presentation. After that, please collect all your questions. After that, Ruslan will answer them. And then the second part is going to be hands-on section. Okay, so Ruslan, it's all yours.
Sounds good. Thank you, Yuri, for the introduction. I'm going to take over screen sharing now and share my slides. Okay, hopefully you should see my slides now.
Yes.
Well, thank you, everyone. Thank you for having me. It's always great to come back to Argonne even virtually. Before I get started, as Yuri said, questions in the chat are good. If there's something pertinent, don't hesitate to just unmute and jump out. I don't think there's that many people on this call, so that should work. It would be great to make this as interactive as possible. And I think that's all of the logistics, so I'm just gonna go ahead. All right, so let me begin by making some high-level statements about the scope of what we're doing here. You know, in general, when we're thinking about the complexity of solving optimization problems, or problems in general, really, we're usually interested in how this complexity, the time or memory requirements grow with problem size, or there's the asymptotic complexity of your problem. And our famous classes of problems are P, so problems that are solvable in polynomial time, so something like max flow min cut. Then we have NP class of problems where we can verify the proof of the solution in polynomial time. So famously, integer factoring is in NP because you can just take the two factors and multiply them to check that the solution is correct. And finally, the larger space is P space, so problems that are solvable in polynomial space without any requirements on time. And the quantum complexity class that we will be most interested in is BQP, bounded area quantum polynomial time, which is problems that are solvable on a quantum computer in polynomial time with an error probability of at most 1/3 for all instances. And this BQP is, for our purposes, simply, you can think of it as a quantum analog of the classical P class. And this is how you can sort of picture them graphically on a Venn diagram. So something like the shortest path problem will be in class of P because it's solvable in polynomial time. Something like integer factorization will be somewhere there because we know that it's at least at NP, but it may be in P, and we don't. It's one of those famous NP intermediate problems. And something like maximum cut problem, which we're going to talk about today more, is an NP complete problem. So any problem in NP is reducible to it. Now, the reason I bring this all up is that all of these statements about hardness, like the hardness of the maximum cut problem here, are in the worst case. So for example, for certain instances, like maximum cut problem on a cycle graph, problem is actually very easy, right? It's just take every other vertex. So the complexity of particular instances of your problem is less clear often. And more generally, those instances that trigger the worst case complexity bounds, or classes of instances that trigger the worst case complexity bounds, are not always easy to construct, and proving asymptotic performance is even more difficult for the kinds of algorithms that we will consider. And so the takeaway here of this first few slides is that we are not going to use QAOA to solve NP-complete problems in polynomial time on quantum computers. If you take just one thing from this tutorial, maybe it should be this slide. Now, so what are we then going to do? Well, what we're going to do is we're going to adopt a slightly different perspective on these things. So think about classical algorithms that work well. So you can think of them as sort of falling into two classes. You can have classical algorithms that have proven performance. So like that algorithm for shortest paths that I mentioned earlier, or the matrix multiplication, which always runs in, n to the power of like 2 point something. But for many problems, and there are quantum algorithms like that too. So algorithms like short in algorithm for integer factoring as provable asymptotics and a provable speed up over the best classical algorithm that we know of. However, for many problems that we're interested in, the methods or the algorithm that work best do not have these properties. So for example, most, like all the algorithms used in classical machine learning, a lot of them do not have provable guarantees on the running time. Such is the case, for example, if you apply gradient descent to a problem that you cannot guarantee is convex, which we do all the time, of course, and it works quite well. Or something like a genetic algorithm as a heuristic. And these algorithms are very powerful classically, and they're used all the time. And there's no reason to think that in the quantum case, it would not be the same. So the quantum heuristics, like quantum annealing or QAOA, which we're going to talk about today, or maybe more others. Maybe quantum annealing in particular is not so promising, but there are many other quantum heuristics that are going to be discovered. And now that we're starting to get our hands on this quantum hardware that is approaching the limits of what you can simulate classically, now we can leverage this unique opportunity to develop these heuristics and actually numerically evaluate them. And today I'm going to talk about one such heuristic, which is the QAOA algorithm. Okay, so with that out of the way, we can switch gears and actually talk about QAOA. But I'm going to take 30 seconds to see if there's any questions so far. Okay. So the way we're going to do this is we're going to start with the maximum cut problem, which is sort of this very nice paradigmatic example of how to solve computer optimization, how to map computer optimization problems to QAOA. And then I'm going to talk briefly about how to do this more generally. Though now, if you go on the internet, you can probably find examples of these mappings for many, many problems very easily. So what is this maximum cut problem, or max cut? The goal of maximum cut is to split the set of vertices V of a graph into two disjoint parts such that the number of edges spanning two parts is maximized. So for example, here on the right, if we have in this 4-node graph, we have the green vertices in one part and red vertices in the other part. And so we cut these 4 edges. And we can formulate as an optimization problem by assigning to each variable a spin, or a variable that's simply, to each node, a variable that's simply plus or minus 1. So spin up or spin down with this objective function. And it's easy to see that this is the correct objective function by just observing that if the edge has variables of the same sign on its ends, then the contribution to the cut is 0. And if the sign is different, then the contribution to the objective is 1. Okay. So now we have to have to solve this classical optimization problem on a quantum computer. And to do that, we're going to take our classical objective that we just written, and we're going to formulate it. We're going to formulate this problem of maximizing this objective as a problem of characterizing some quantum Hamiltonian, some Hamiltonian, which is simply a Hermitian operator for those of you with more mathematical background. So we're going to take our objective, which is we're finding the string of vectors, the string of plus and minus ones that maximize our objective, and we're going to turn it into a problem of preparing an highest energy eigenstate of this Hamiltonian, or equivalently, in mathematical terms, this is highest eigenvalue, or equivalently, in mathematical terms, this is highest eigenvalue, eigenvector. Now, since this Hamiltonian is classical, if we can do this, if we can solve this problem exactly, we can prepare this eigenstate on a quantum computer, then we can measure it and get the solution with certainty. So there's no randomness at the end of it, as long as we can prepare the eigenstate exactly on the quantum computer, which in practice, of course, we often cannot. Now, what does this Hamiltonian look like we're trying to prepare? Now, first, it's diagonal, so it's a diagonal matrix, and it has on its diagonal values corresponding to the values of objective function on all binary strings, or in quantum terms, on all computational basis states. And so if it acts on a computational basis state, let's say all zeros, so vacuum state, then what it comes out is the value of that subjective function on the corresponding binary string. So in general, this Hamiltonian acts on computational basis state by adding a factor equal to the value of the objective function of this binary string. And this is the operator we're trying to build. This is the operator that we're going to say we're going to represent on qubits our objective function, our classical objective function. Now, one thing you can immediately note is that it's a 2 to the n by 2 to the n matrix, right? So we cannot construct it explicitly. Otherwise, we could just go on the diagonal and pick the best value already. If we held this as a matrix, there's no point in doing this. So we're going to do this implicitly. And this is our next question. How do we construct this Hamiltonian? Okay, so just quick notation refresher. So we're going to denote by ket. So this letter X jammed between arrow pointing to the right, a column vector, and by bra, which is this y vector, and it's inside this funky looking brackets pointing to the left, the conjugate transpose of that. And then our inner product can be written as bra y ket X, which is simply inner product of the corresponding vectors. An outer product is going to be written as ket X bra y. And again, this is just standard linear algebra, standard outer product, which gives you out a matrix of the size, length of X, length of Y. This is the direct notation. It is no different than making X boldface or putting an arrow over X. So if you see it for the first time, don't be confused. All you need to remember is that if X points to the right, it's a column. If arrows point to the left, it's a row. Okay, so let's recall our max cut objective again. Now, what we're going to show is that all we need to do is we need to take each binary variable here and replace it with Pauli Z. And this formula, resulting formula, will just give us the correct Hamiltonian. So essentially what we want to show is we can just simply take, can simply map binary variables onto the eigenvalues of Pauli Z. Okay, so this is what we're going to show now. And specifically, we want to show that it does indeed correctly represent our objective function on qubits. So we want to show that C acting on ket X is equals to C of X ket X. Okay, so first things first, what is a Pauli Z operator? Pauli Z operator is simply this matrix that's diagonal, has 1 minus 1 on the diagonal. And then we can easily check that it has eigenvalues -1 and +1 with eigenvectors being the computational basis states. So if you apply Z to state 0, we get state 0 out. And if we apply Z to state 1, we get -1 factor in front of 1. So more generally, Z acts on a computational basis state X is as -1 to the power of X, where X is just a single qubit computational basis state. Now, if it acts on, let's now go to more general case of n qubits. If it acts on ith qubit, we'll get -1 to the power of xi. And this is simply because when we write zi, this is really a hidden notation to show that we're really writing identity tensor product, as many identities as we need. Zi tensor product as many identities we need on the other end. Now, if we have products of these two, so we have zi, zj, and they're acting on this computational basis state, then what we get out is -1 to the power of xi, -1 to the power of xj. And here we reordered qubits so they're adjacent, so we can write this nicely when we pad it with enough identities on both sides. Okay, so this is power z. Hopefully you're already catching what I'm getting to, but let's still walk through it very carefully and very slowly, so we're all on the same page. So we're saying that this is going to be our Hamiltonian. We're claiming that this is our desired Hamiltonian. So let's start by reformulating our classical objective. So we're going to do a simple variable change. So we're going to go from si -1 + 1 to xi 0 or 1. And this is simply by saying that xi is 1/2 1 minus si, which is the same as this linear substitution, which is really the same as saying it's -1 to the power of xi is si. All right, so we go from si -1 + 1 to -1 to the power of xi, which is also -1 + 1, and xi is 0 or 1. And this is then our new objective. So now hopefully it's clear what we're doing here, because this is simply the action of Pauli Z of zi zj on computational basis state X. And we can just verify it directly by taking this Hamiltonian and hitting Pauli X with it. What we get is, first by linearity, we can unroll it into this. So the first thing, identity acts on X, is just identity, and zi zj acting on X gives us -1 to the power of xi, -1 to the power of xj. And so this is exactly the correct value. This is the objective function value on the binary string X. And so with that, we are all done, and we have shown indeed that this is the correct Hamiltonian to represent our max cut objective on qubits. And note that nothing about our procedure that I just outlined is really specific to the maximum cut problem. The same procedure would work for any other Hamiltonian, any other classical objective defined on spins. Now, one question you may have is, what is the size of this operator? Now recall that when we write this zi zj, it's padded with identities on both ends. So it's really a to the power of n by to the power of n matrix, which would be possible to write out explicitly, but we do not. We write it out as a combination of Pauli Z's, and then the Pauli Z's we're going to implement on hardware. Okay, and this will be a good time to stop for questions and see if there's any questions from the audience.
Excuse me. It's not clear to me that even if you find a configuration which optimizes the Hamiltonian, there exists a physical cut which will realize this configuration. Like, can you always draw a line that through this graph that will implement this configuration?
Right. Okay, that's a great question. So let's let me see if I can, if I broke my preview. Okay, it's working again. Okay, so when we prepare this configuration and we measure it, right, we will get out some binary string. Okay.
Right.
Right. So, and then now let's see quickly that any binary string encodes a cut of the graph, right? So we go from, so binary string, we measure out something like, measure out in, let's say we measure in Z basis, right? And we get -1s and +1s. And then each of these combinations, each of the measurement outcomes we get encodes a cut on the graph, because it simply means this vertex gets assigned to part 0, this vertex gets assigned to part 1, and so on. Does that make sense?
So it always exists. Such a cut always, there's always a cut corresponding to a configuration.
Right. Any combination of -1s and +1s, or 0s and 1s equivalently, encodes a valid cut. Yeah. So this problem has no constraints.
I see. Okay, thanks.
Right. And that's a great question, because in some problems like graph partitioning, you have certain constraints on, for example, your parts have to be equal, right? Then then you have to deal with those constraints because some binary strings will not encode a valid solution.
I see. Thank you.
Thank you. Okay, there's no other questions. I will go ahead and talk about the more general case. Now, so we construct this Hamiltonian for this very specific function. Now, can we show that they exist in general, right? So say you have some arbitrary function defined on the Boolean cube. For simplicity, it's unconstrained. Can we always map it to a Hamiltonian representing it on qubits efficiently? And what I'm going to talk about briefly on the next few slides is a method from this paper by Stewart, which is this nice, which shows this nice existence proof essentially. But in practice, so this is more theoretical and has to do more with the showing that there exists such a mapping. Okay, and the technique that we're going to use is Fourier analysis of Boolean functions. So let's start with the example of maximum function. It's a function that takes the maximum of 2 bits, for +1 +1 returns +1, or -1 +1 returns +1, and so on. So we're going to convert it to a function on 0s and 1s instead of a function of spins. And then we're going to express it as a multilinear polynomial, which has up to exponential number of terms. Now, how do we construct this multilinear polynomial? And note that once we have the multilinear polynomial, we're actually essentially done, because then we can just use the same techniques as before. So to construct this multilinear polynomial, note that we can write this f of x as sum of f of I times the indicator polynomial that takes the value 1 if x is equals to a and 0 otherwise. And this indicator polynomial can be directly constructed as follows. So for example, for the maximum function, you can construct these indicator polynomials for all 4 configurations, and you will get out this multilinear polynomial encoding your maximum function. And then for each monomial, let's write this as, let's introduce notation where x to the power of set s is just product of xi over that subset. And this is simply to write neatly these monomials. And then this written like this as sum over s monomial corresponding to s and the value of the function on this s. This is the Fourier expansion of our Boolean function maximum. And the Fourier coefficients are given as follows. Now, since for every function defined on the Boolean cube, there exists unique such Fourier expansion with then essentially we can use this unique Fourier expansion to construct the quantum Hamiltonian always. Now let's quickly see how to do this. So we want to construct a Hamiltonian such that when we hit a computational basis state with it, we get out f of x times that computational basis state. Or we can write out in the terms of the Fourier expansion. This is what we want to get. Now, note that the products of Pauli Z operators implement parity functions. So if you act on x with product of zj over this subset s, then you get x to the power of s x. And this is simply because each of them will contribute xj, so plus or minus 1, and then product of them by linear is going to be just product of the result. And so the unique n-qubit Hamiltonian representing f is just given by sum over these s with Fourier coefficients and products of Pauli z's over corresponding subset of indices. So this gives us a general recipe that we can use for this existence proof. So we take our objective function, we perform its Fourier expansion, and then we take the coefficients and we use them to construct the unique n-qubit Hamiltonian representing it. Now it's a general recipe, so it's an existence proof, but it is potentially not efficient. That is, in the worst case, it's going to be very hard to compute this expansion, and it will be a large expansion too. So in practice, this existence proof doesn't perhaps matter too much to you. And in practice, what you want to use is you want to use these building blocks, where you can code certain building blocks from which Boolean formulas are typically built into corresponding Hamiltonians. And then from this, you can combine and construct your desired objective. Okay, and this covers how we take our classical optimization problem and we convert it into a Hamiltonian that we are then going to characterize on a quantum computer. Any questions so far? All right. So in the remainder of the talk, by the way, feel free to, if you can also unmute yourself and ask questions if you have any questions throughout. Chat is also there. So for the remainder of the talk, I'm going to talk about how we solve this problem with QAOA. So what is QAOA? So what we're going to do is we're going to prepare a parameterized state of the following form. And this is going to be our QAOA parameterized circuit or QAOA ansatz. And ansatz just means trial state. So we start in vacuum state all zero, same as same as most textbook algorithms. Then we apply a layer of Hadamard's. And then we apply pairs of these alternating operators, where one of them is exponential of minus I gamma c. So c is our operator encoding their cost function. So this is just time evolution with the Hamiltonian encoding our cost function. The second one is a time evolution with this Hamiltonian, which is called mixer, which essentially mixes together the probability amplitudes of different quantum states. And we just repeat that for a bunch of times, this layers of alteration operators. And we let the evolution times parameters be a free parameter. Then typically we have some sort of procedure to optimize the expected objective value of the measurement outcomes of this quantum evolution. So we're trying to find this beta and gamma, these parameters, which define the length of the time evolution with these operators, with these Hamiltonians, such that we want to maximize this expected value of the objective function. And we can have either an outer loop classical optimizer that just does like gradient descent or something like that, or you can have, in some cases, you can write them out with pencil and paper, and in some cases you may want to have some machine learning procedure that predicts them. So this need not be variational in principle. Now, why do we think this is a good thing to try? Well, for infinite number of these alternation layers, what you can do is at the very least, you can exactly approximate a diabatic quantum evolution. And so if you perform a evolution adiabatically for sufficiently long time, you will prepare the desired state and you have a guarantee that that will happen. Now for small p, the picture is a bit more mixed, but there's still some indication of potential for quantum advantage, which I'm not going to dive too deep into here. So how do we implement this circuit in gates? Of the kind of gates that the tutorial Monday talked about. So we're going to assume the following pretty standard gate set. So we have the Pauli's XYZ, we have the Hadamard gate, which I already mentioned, phase gate, and rotation around z-axis. which is also a pretty standard gate and often as native on hardware. Okay, so let's start with a very simple operator, where we just want to do time evolution with Pauli Z. Let's see quickly that it's just equal to RZ of with the rotation angle being 2 times the time evolution. And to see this, you don't really need to do much more than the squint at the definition of RZ and know that the definition of RZ is equal to exponent of minus I theta Z over 2, where the RZ is rotation with the angle theta. And this is because it's just diagonal matrix. So having squinted at that definition, we quickly realize that our desired circuit is just one RZ gate. And so this one RZ gate implements this, this operator. Now let's make it a little more complicated. Let's do 2 Z's, okay? So I want to implement time evolution with a product of 2 Z's, which is, just as a reminder, it's tensor product of them. Now, to see how to do that, recall that if, since Z has eigenvectors 0 and 1, the eigenvalues 1 and -1, then exponent of Z is going to have the same eigenvectors and eigenvalues. And this is true for any matrix. Then the desired, we can write out the action of this operator in the conventional basis to see what is our desired operator. So for Z 0, 0, we want to get exponent of minus IT 0, 0 out. For 0, 1, we want to get exponent of IT 0, 1. For 1, 0, we want to get exponent of IT 1, 0. And for exponent of 1, 1, for this acting on 1, 1, we want to get exponent of minus IT 1, 1. So what this operator does is it adds a phase with a sign depending on the parity of the bits. So in general, what we want to do is to do something that adds this phase, and the sign of the phase depends on the parity. Now, what the circuit that does this is this circuit. So C0, RZ C0, and we can quickly check that this is indeed the case. So after the first C0, we get A and then A XOR B. Then the RZ adds a phase depending on the value of the second register, which is A XOR B. And then the last C0 returns the second register to its original state. And now we have this global phase that is our desired phase, and AB. So this circuit implements the desired operation. And this is how we implement the time evolution for ZZ. Now, this is we're essentially done with the phase operator at this point, because all terms of our Hamiltonian commute, which means we can just unfold the sum in the exponent into product of the corresponding operators and get a circuit that looks sort of like this. So the circuits can be just concatenated. There's nothing special that needs to be done here, because all Pauli Z's commute with each other. And with this, we can simulate the operator corresponding to the problem Hamiltonian, because all it is some linear combination of those ZZ terms with maybe some identities, but those are irrelevant. Okay, so with this, we can simulate half of the circuit. We can implement half of the circuit in gates, the part of the circuit that corresponds to the cost of phase operator. Now, how do we implement the mixer? So let's start with one term of the mixer, which is just exponent of minus I xt. So time evolution with Pauli x. If you do the series expansion of exponent of minus I zt, and you jam it between two Hadamards, what you will see is that what comes out is simply the series expansion of exponent of minus I xt. And so what the simple observation shows us is that all we need to do is to jam the circuit for exponent of minus I zt between two Hadamards, and it'll give us the desired circuit. And if you have a more complicated mixer, you can play around with tricks like this to try to derive a circuit for it. Though in general, of course, it gets much more complicated. Right, and this is our circuit then, Hadamard, RZ of 2T Hadamard. And this is the entire QAOA circuit. So now we know how to implement the full QAOA circuit. Okay. Now, as I mentioned earlier, QAOA prepares a parameterized trial state that is a function of two parameters. And so we start in uniform superposition, and we try to vary these parameters beta and gamma to prepare the state that is our target state, which is the eigenstate of our desired Hamiltonian. And from this geometric picture, it is hopefully clear that the quality of the QAOA solution will depend crucially on our ability to find these high quality parameters, either using a classical optimizer or otherwise. And we'll talk about this a little bit during the hands-on. Okay, let me switch gears and talk a little bit about the connection to the adiabatic quantum computation. So in the adiabatic algorithm is simply a way to prepare ground state or highest energy certain eigenstates of the target Hamiltonian, which is inspired by the adiabatic approximation algorithm, the theorem, sorry, which state roughly that a system prepared in an eigenstate of some time-dependent Hamiltonian will remain in the corresponding eigenstate, provided that the evolution is performed in scare quotes slowly enough. Or slowly enough typically means like something like 1 over the eigengap squared, for example, for the ground state. And so the idea behind this adiabatic algorithm is then to start with an eigenstate of some simple Hamiltonian. In chemistry, it could be Hartree-Fock, or here, it's something like the transverse field, Pauli X null cube. It's very simple Hamiltonian, and then slowly evolve your system to keep it in this eigenstate, so that at the end of it, you will get the eigenstate of your desired problem Hamiltonian. And so your interpolation is performed by this time-dependent Hamiltonian, where S of t is some smooth function of time. That's so with only constraint that you start in your simple Hamiltonian, you end in your desired Hamiltonian. Right. And so in our case, our simple Hamiltonian will be the Pauli X, so same as in QAOA, because its ground state is simply uniform superposition of all computation-based states, and our target Hamiltonian will be our max-cut Hamiltonian. So how can we simulate this time-dependent Hamiltonian in a quantum computer? So let's quickly recap some basic things. So in general, our quantum evolution is described by a Schrödinger equation. So time derivative of your state, I is equal to Hamiltonian applied to this state, which is solved by exponent of minus I integral from 0 to t, h of t dt. Okay, this is probably the first differential equation you have to solve in your differential equation class in undergrad. Now, this thing is time dependent, which is hard. So let's break it up into small time steps and assume that on each time step, Hamiltonian is roughly constant. And so this gives us this product of exponent of minus I h j delta t, where this is, well, delta t is small, so that h is constant on this delta t. Now recall that our h is actually this time-dependent Hamiltonian that has two terms in it. Okay. And the one term is our initial Hamiltonian, and the second term is our target Hamiltonian. And so this is inside every time step. So what we're gonna do is we're just gonna do Schroeder approximation with one step of simplicity. So we're just gonna say that it's about the product of them. Okay. And so at each time step, we're gonna say that this is approximately equal to the product of exponent of our first Hamiltonian times exponent of the second Hamiltonian. And then we're doing this product overall over our discretization of the time. Now, if you squint at this circuit, and I know there's a lot of squinting in this tutorial, but I appreciate it. If you squint at this operator, which implements our adiabatic evolution, you see that it's exactly like our QAOA circuit. So the outer product is because we took these small time steps to make our time-dependent Hamiltonian constant each time step. And internally, we have two operators because we took this approximation where we approximated the exponent of sum of two non-commuting things by their product. And so what we see here is that QAOA with certain choice of beta and gamma is equivalent to simulating adiabatic evolution. And this is why we can say that, okay, in the limit of infinitely deep circuits, QAOA can at least approximate the sufficiently slow adiabatic quantum evolution, and we can recover the optimal state. Now, in shallow depth, when it's very non-adiabatic, the mechanism is quite different. But this is the motivation that there exists this limiting behavior. And so QAOA is an interesting answer to try. Any questions so far?
What is the reason for choosing the initial Hamiltonian to be in this particular form? Is it any significance in that?
It's easy to prepare. I think that's it. Yeah, I mean, you can, yeah.
I see. Yeah.
It simply needs to not commute with your target. I think that's really the only constraint, because otherwise you have trivial dynamics.
I see. Thanks.
So this last part, I think I'm actually going to skip because it's perhaps not that interesting for this audience. But you can evaluate this value of the objective, often classically, if your target operator is sufficiently sparse. But I'm just going to skip this and summarize what we talked about so far, which is, first, we will not solve NP-complete problems. We're not solving NP-complete problems in polynomial time. If somebody tells you otherwise, don't believe them. However, QAOA is a promising heuristic for the NISQ era. And there's been a lot of recent, very interesting numerical and analytical results showing hints of the potential for quantum advantage. To solve a given optimization problem, we need to map it to a quantum Hamiltonian, which we can always do in principle, and often is very easy to do in practice. And the reason to think that QAOA is an interesting ansatz is, one reason is that in the limit of infinitely deep circuits, we can approximate exactly the adiabatic quantum evolution and recover the optimal solution exactly. And our next step is the hands-on. I think this URL is incorrect, but you have the correct URL that Yuri has shared earlier. So I'm gonna stop my slides. And while I switch to sharing my Jupyter notebook, you have another minute to think of questions.
Yeah, I had a question, Ruslan.
Yeah, go ahead.
I was wondering if you can go a little bit more into the purpose of the mixing Hamiltonian. It's maybe, yeah, I didn't explain it a little further. Why do we need it there?
That's an excellent question. So think about it this way, right? So your cost Hamiltonian, the Hamiltonian that encodes the objective function, is diagonal. So what does it mean that it's diagonal? It means that all it does is it adds some phases to the amplitudes of your quantum state.
Right.
Right. So no interference happens. Like if you just do the cost and you measure, it's the same as random guess because those phases you cannot see if you measure on the Z basis. What the mixer does is it enables this constructive and destructive interference between the probability amplitudes of different solution, which actually helps you solve problems.
I see. Yeah. Is this the, like, by applying the poly X, is that the only way you can construct mixing, or can you do it
No,
Or
no,
is
no.
it just like the easiest way to implement?
There's many ways to do it. So one, imagine a setting where you want your solution to have a certain Hamming weight. So say, you're solving a portfolio optimization problem and you want to pick, exactly 8 stocks, right? So you want your Hamming weight to be always 8.
Mm-hmm.
In that case, you don't want to use the X mixer because it'll just mix together all probability amplitudes, and it will not guarantee that your output is going to be Hamming weight 8. So instead, you can use a mixer that's it's written as it's time evolution under XX plus YY, which if you write it out explicitly looks like a swap. It's almost like a sort of parameterized swap where you're rotating, between 0, 1 and 1, 0. So that's an example of mixer that would preserve your Hamming weight.
Oh, so it doesn't necessarily have to be like a 1-qubit gate, the mixer.
Yeah, in general, you just want to connect the probability amplitudes of all of your solutions, right? So you want to have a mixer that connects, sort of everything sufficiently.
Okay. All right. Yeah, I just thought that maybe it was always the case that with your mixer you needed to have that the poly X, and yeah, I understand how it can be problem specific now and how you can change the mixer too. Thank you.
And thank you for your question. Any other questions?
Hi, I also had a question as well. So it's about the Fourier expansion for the desired function at the beginning. So were you able to do that for the Boolean functions by sort of, because it was periodic, and that's how you could do the Fourier analysis stuff with that, because you could use the periodicity of it? Is that how you were able? It just wasn't super clear to me, so maybe just I was a little confused there.
No, it's a great question. It is a little bit confusing because really the only reason we're bringing up this Fourier analysis connection is because the Fourier series expansion always exists, right? For a given function, somebody else has proven. I don't actually know the technique for proof of how it works, but it always exists, right? And you, I think, you have this like explicit way of constructing it, which is in principle, inefficient. In practice, of course, we're not doing it like that. Right? In practice, we have some classical objective function that is already written as a polynomial, and we just take this polynomial and we convert it into some polynomial and Pauli Z's, and we're done. But to your question, how do you write a Fourier expansion for an arbitrary function? I think the only answer I can give you, which is maybe somewhat satisfying, is, let me go back to the slides very quickly. So this partially satisfying answer I can give you is that you just simply do this. Yeah, you just write it out with, you have your value of the function on A and then indicator polynomial on A. And the indicator polynomial you can always construct explicitly. Right, so this way, if you take all possible exponent to the power of n binary strings, you can explicitly write out this polynomial.
I see. I think that makes more sense to me. Yeah. With writing it through the polynomial. But okay, yeah. Thanks.
Thank you for the excellent questions. All right, if there's no more questions, by the way, again, do not hesitate to just unmute yourself and speak up if you have some questions. But if there are none at this point, let's proceed to the hands-on. So I pushed the latest notebooks only like 30 minutes before the tutorial, but I think there's been actually no changes. Just need to install the dependencies, which is Qiskit. and Qiskit optimization, and SciPy for some reason does not get. You need to update SciPy because some things break with the latest SciPy. Okay, so with that, you should be good to do the hands-on. Let me see if I can start. There it is. So, oh, no. All right, never mind. So is this big enough for everyone to see?
Yes, it looks good.
Thank you, Yuri. So recall that we're solving this objective. So we're finding some binary string S that maximizes this objective function. And we're going to just go ahead and drop the constant terms because when we implement this on hardware, they don't show up, right? They're invisible to us. So we're really going to just solve this optimization problem, which just has this minus SISJ in it. And then the constant offset we can always compute later. So to solve this problem, we need to construct the Hamiltonian representing it, which is given by sum of our edges minus the IZJ. And so what we want is we want to have a QAOA circuit with this Hamiltonian and the mixer that we talked about earlier. And we want to run it in simulation. And so for this, we need to implement the cost of the mixer operators, which we're going to do, which we talked about how to do theoretically, but now we're going to do it in Qiskit in no time at all, actually. So let's start with some toy graph. So consider this graph. It's just bipartite graph, K32, complete bipartite graph. So let's start by building the circuit for the cost operator, which is exponent of minus I gamma, sum over ij, zij. The way we're going to build this is very simply. So we're going to start with an empty quantum circuit for this, just for this operator. And for each edge, we're going to append this term corresponding to this exponent of zij. Remember, because they all commute, we can unfold this into a product of their exponents. And the circuit to implement each zij term is simply C naught RZ C naught, as we talked about before. Now we can take this function and check that it indeed produces the correct circuit. And we do get the correct circuit, C naught RZ C naught, C naught RZ C naught, C naught RZ C naught, and so on for each edge in our graph. And this is the circuit for our cost operator. Now the second thing we need is the mixer operator, which again, everything commutes with everything. So we can just unfold it into a product of corresponding operators, and each of them is a single qubit time evolution of Pauli X. So to construct it, for each node in our graph, we add a term to the circuit, which is corresponding to this Pauli X. And this term is simply Rx, right? Here we have this native gate, that's Rx. I mean, you can also, if you only have RZ, you can write Hadamard, RZ, Hadamard. But in this case, we don't need to deal with that decomposition. And our mixer operator circuit is now simply, Rx on each gate, on each qubit with a corresponding rotation angle. And now we can build the full circuit. From these building blocks, we can build the full QAOA circuit for a given graph and parameters beta and gamma. So we infer the number of QA steps from the length of beta. We start with an empty circuit. We begin by adding Hadamard on each qubit. And then we apply these P alternation operators. First, the cost, we append the cost, and second, we append the mixer. And finally, we measure at the end. And that's our entire circuit, which we can nicely draw and see. If you add barriers, it looks a little bit nicer, but here you can see the initial layer Hadamards, then you have the C naught RZ C naught, and then in the end you have this Rx on each qubit, and you see them for each qubit as you expect. And finally you measure. So this is our full QAOA circuit. Now, for the when this tutorial will only run stuff in simulation, mostly because it's just much easier and more pedagogical. But the same code works on hardware. So if you want to, after this tutorial, go out and run your circuits on hardware, that's very easy to do. All you need to do is to change the backend that you use. Another thing that you need to be careful about is that Qiskit uses an ordering where 0th qubit is the rightmost. So it orders qubits, numbers qubits from from right to left, which is different from standard math notation of left to right. And so when we get the counts, measurement counts from quantum computer, we need to invert them. But with this out of the way, we can run our circuit on the simulator backend and get the counts. And these are our counts. And it sort of looks like, random noise because we did not optimize the parameters beta and gamma. We can indeed evaluate the quality of this solution by computing the expected value of the objective function from these measurement outcomes. To do that, we need to have a function that maps a binary string and graph to the value of this max cut objective, which is this. Simply, it adds 1 to the cut if the 2 bits corresponding to a given edge are not equal. You can easily check that this is our optimal solution. It gives us -6, which is the maximum cut we can have on this bipartite graph. We cut all edges. And from counts, to estimate our objective from counts, we go over all binary strings and number of counts for this binary string in our dictionary of counts, and we simply compute the average. And so for our simple sample where we hard-coded some terrible parameters, we get -2,925, right? Whereas we expect -6. Note the minus here is simply because we want to minimize. This is just convention optimization literature. So this is not too great of a solution. Now to get a better solution, we need to optimize the parameters beta and gamma. And to do this, in this case, we just simply use some SciPy minimize optimizer. We use Kabbalah. You can use many much better optimizers out there. So to optimize the parameters, we need to wrap the objective into a black box to be passed to this minimizer. And it's exactly what we do here. We build this F that takes theta and returns the max cut energy. Now this black box objective, we can just now take and pass to SciPy minimize. And here I'm not rerunning everything, but if you run this, hopefully you get the same number as me, which is something like -5,297, which is not too bad, right? So remember our optimum is -6. So this is not too far from the optimum. Now let's look at the count. So let's take the circuit and rerun it again with the optimized parameters. So we pass our pre-optimized beta and gamma into the circuit. And we can look at what are the binary strings that we've measured out. So we can plot them, this histogram, where on the x-axis we have different values to the objective function. And the y-axis we have number of samples with this value of the objective function. Right, so ideally we have everything that's only 6, there's nothing else. But in this case, we have some solutions that are outside, that are not optimal, but overall, this is pretty close to optimal. So this is quite good. Most results we get correspond to good solutions. And if we take the best solution, so the solution that gives us the minimum objective over all the solutions we measured, this best solution, if we draw it, it looks exactly like we expect. It's the correct optimal solution. All red nodes are in one part and all blue nodes are in the other part. And the optimal solution has cut 6, as we expect. Now, we can also look at the full QAOA state in Qiskit, as you may have learned on Monday, which is the full vector of these amplitudes. We use some helper functions for this. This really has to do with dealing with endianness in Qiskit, that issue that I mentioned earlier of qubits being ordered in the opposite direction. from what you would expect intuitively if you come from, like undergrad math sort of perspective. So we can get this circuit, and we just gotta do it with no measurement in the end. And we can get the same sort of dictionary by just taking our state vector, converting it to a dictionary of amplitudes, just something so it looks very similar to our counts previously. And if we run it on state vector simulator, we get some vector, these amplitudes. We can sort of see that the amplitudes that are larger. So where's our optimal solution here? It's this one is one of our optimal solution. We can see that it has large amplitude. And our another optimal solution is this one, and again has a large amplitude. So we can examine directly the amplitude of our state vector. And we can even check that we get the same energy, which is always a good check to have. Okay, so what is the difference, right? Why would we want to run this and compute the energy from the full state? Well, let's just rerun the optimization and do this again. So we're going to do this objective again, and we're just doing everything the same, except we changed the simulator. Now we use the kind of simulator, and we run the optimization, and now we get something that's very, very close actually to the true ground state. All right, so here we got some 595. Hopefully at home in your notebook you get similar results. So this is very close to the optimal, much closer than the previous one. So why is that? Well, it turns out you get this much better solution if you run with state vector, because if you use the samples, the optimizer will get stuck in some lower quality point. Now you can see that these parameters are quite far apart from each other. For example, for beta, you can compare the value found by optimizing the objective computer from samples and optimizing the objective computer from the full state vector. These are quite different numbers. So our optimizer, when optimized against objective samples, is getting stuck in some low quality local optimum. And this is because essentially the sampling noise throws off the deterministic optimizer we use. And so it thinks it's in the local optimum, but it's not. In the local minimum, but it's not. And in fact, we can see that by taking this initial point and running compiler from that initial point that we obtained from the objective with samples with tiny initial step. And if it was truly a local minimum, we would not be able to improve upon it. However, here with the state vector simulator running from the same initial point, we do indeed get a better energy. So we get 537, and we used to have 529. So we improve on this objective, even though classical optimizer, the optimizer that was using the samples, got stuck there. And the lesson here really is that if you're using deterministic optimizers like Kabbalah or many others used in, if you find in like SciPy Minimize, they assume that every function value they get is true. So that causes them to think that a point is a local maximum, even though it's just some stochastic noise, making the objective function higher than it should be. So in simulation, often it's a better idea to use the full state vector to optimize the energy, just because it has the smoothness. There's no stochastic noise into it. But in the long term, you should use stochastic optimizers, and those exist. There's people doing work on stochastic optimizers that are specifically tuned for quantum optimization. Now, in practice, there are simpler ways to build this Hamiltonian. So here we build the Hamiltonian in the circuit for it from scratch, but you can do this in Qiskit by constructing some quadratic program encoding your objective. Right, and here we just build this quadratic program where it has the linear and quadratic terms. This is our max-cut objective, and this returns us some Ising, which looks like exactly what you expect, right? So remember it's 1/2 sum over edges minus zi zj, and here if we print this cost operator that was produced by Qiskit, we see exactly this. So there is a zz term for each of our 6 edges. And the way we got this cost operator again is we build a quadratic program and we passed it to this constructor. And then we can just generate QAOA ansatz from this operator using Qiskit and plug in the parameters. And then, for example, this we can wrap in a black box function and optimize parameters, or do whatever we want with it, as the same as we would do with the QAOA circuit that we implement ourselves. So now, if you have quadratic program that is already implemented in Cplex, good people at IBM has been making a lot of effort trying to make your experience more smooth and being able to just take your Cplex objectives and formulate them as Hamiltonians to be used in QAOA. But before we do this really from the ground up, just so it's very, very clear to everybody what is the actual circuit that we're implementing. Well, with that, let me know if you have any questions. This is all I have. I'm happy to stay longer and chat.
So any questions? Please use chat or just unmute yourself. Maybe I'll ask, well, actually, while we're waiting, these are kind of like a common type of questions that we get. So the Hamiltonian is already diagonal, right, Ruslan? So it's a it's basically a trivial problem already. So what is essentially the challenge here?
Right, so the challenge is you do not hold Hamiltonian explicitly. You hold it written as some combination of Pauli Z's, because of course, if you had the Hamiltonian written explicitly, there's no problem to be solved, what you correctly said.
Right. So essentially, to solve it correctly, you still need to essentially enumerate it, right? Essentially, go through all solutions, right? And that's basically the challenge here, right?
Right.
Yeah. And the second kind of common question is really how quantum noise affects QAs, right?
That's a great question. I think Dan is going to talk about it on Friday. Is this a flag for the next tutorial?
No, then we'll just provide general introduction to quantum noise. I don't think he will touch base QAOA.
Yeah. Well, it makes everything harder. So if you think about the problem of parameterization, right? So we had this issue where stochastic noise would throw the optimizer off and it would get stuck in the low quality solution. That's not even a local minimum. It's just like a fake local minimum because of the noise. That problem gets worse if you run on hardware. Hardware imposes essentially a hard upper limit on how many gates you can execute before you're essentially sampling from high temperature gates distribution. So that imposes a limit on how many QAOA layers you can do. Those are the two big ones, I think.
All right. So it is essential problem to this baryon plateau type, right? It's quite sensitive to it, right? Will you agree? Is that
right? So if you have enough noise, all you see is noise, and there's no gradients. So that's the noise-induced baryon plateau, essentially.
Yes, exactly. So it will basically flatten the surface, and basically it will take forever to converge A, right? It will just take a long time, and B, it will most likely converge to wrong minimum or maximum in this case.
Yeah.
All right.
I actually have another question, Ruslan.
Please.
So if you're looking at, for example, if you're looking at an energy landscape in parameter space, you probably find that there's, more than one set of parameters that for a certain QAOA instance give you that max cut energy, right? Is there such thing as within the optimal parameters, like an optimal set of optimal, like the optimal set of optimal parameters, or is it you just have to sort of accept that there's going to be different sets of parameters that give you the max energy?
Right. So one thing to note is if you squint at the definition of the RZ gate, let me pull it up actually. Let me see. So if you squint at this definition of the, yeah, there it is. So if you squint at the definition of RZ gate, so it's periodic. So it has sine and cosine, right? So it's something like pi periodic, I think.
Right.
So of course, you're gonna have, just from this simple periodicity, this trigonometric observation, you're always gonna have some degeneracy in your parameter landscape, right? So that's one source of where you can see this, multiple optima that give you exactly the same solution, and they're not just, they're exactly equivalent. So another degeneracy, if you flip the sign of all betas and all gammas, so you do, instead of time evolution forward, you time evolution backward in time.
Sure.
That's exactly the same thing too. So that's another degeneracy that you will see.
But those are sort of things you can account for, right? In terms of maybe setting, limits on the parameters, or in this case, the angles from, certain values, so that you avoid that degeneracy in periodicity, for example, and also in time reversal. No?
Right. Yeah, exactly. So this is something that you can restrict your domain to keep those things in mind. And then you're saying that within your domain, even after you take into account those symmetries, you still have
degeneracies in the energies for different sets of beta and gamma parameters, right?
I would imagine in most cases you will still have the best ones, the ones that give you the best energy out of them all.
Okay.
Unless there are some other symmetries that are no problem specific or something like this. So this gets a little bit tricky. You can imagine cases where for some contrived graphs, you have more degeneracy in your parameter landscape. Though off the top of my head, I cannot give you an example.
Hi, you were talking about how for when P approaches infinity or is very large, it can exactly approximate adiabatic quantum evolution, but for smaller P, the picture is more mixed. I was wondering if you could expand on, I guess, smaller P and what smaller, like how big P would be for a smaller P, and I guess talk more about the mixed picture, I guess, generally.
Right. So I think the mixed picture really refers to, first of all, it's a great question. So the mixed picture really refers to there are no real proven results there, in the sense of there are no proven results that are like exciting. So there are some results that you need at least certain P to avoid upper bounds. So if you're solving, like high girth bipartite graphs, you can show that you need to have at least logarithmic number of layers. So P that's at least log n to avoid, certain trivial upper bound on your performance. And so, this way, to get advantage, you need at least that many. So that's one class of results. And they essentially come from like counting arguments of, you cannot see cycles that are big enough. And if you cannot see cycles, then you think that you cannot tell apart the cycle from a tree. And so that's where you lose in your approximation ratio. And the second type of argument is you can provide a lower bound on your approximation ratio. So if you have certain depth for certain small depths from just, again, counting subgraphs, you can have a lower bound because you can explicitly write out optimal parameters. Okay, and you're saying that with these parameters, you'll get at least this approximation ratio on this class of graphs. For example, there's results like this on regular graphs. So this gives you some lower bounds, but they're not lower bounds that are, terribly exciting because they don't improve upon, they don't match unique games conjecture or anything like that. I see there's a message in the chat. Yeah.
Yes, maybe I can add. We published a paper basically related to this question. I can see in the chat, it's a link. We're trying to figure out essentially kind of like what the minimum requirements actually for QA to essentially to have a chance to build classical solvers. And of course, there are many variables. It's a rather complicated comparison. But short story long is that our estimate is that you need to have at least P equal 11. to have any chance.
Okay, thank you both.
Right. And another exciting sort of set of results is people are trying to derive these things for SK model. And the best algorithm, there's this Parisi constant. And there's a hope that QAOA can match, best known algorithms, which would be quite cool for SK model. And there seems to be a path to showing that.
I have a question actually can I ask Yuri a question just based on the P equal 11
Go ahead.
cap on is it, I know that that's for the for regular graphs. Do you think it's translates if you go on to random graphs, for example, and this can be like a general question if you determine that you require a particular depth for and this is based on what Ruslan you talked about at the beginning, that based on the type of graph you could have different complexity. So I was wondering if this P equal or higher than 11 for the depth was a general case or just or was it just for the regular graphs?
Yes, so this conclusion was derived for 3 regular graphs and for max cut. If you actually move to like other type of graphs, like weighted, even even stay max cut but make it weighted, the conclusion is very different actually, because the complexity grows actually quite substantially. Or you actually change the problem to like maximum dependent set or free set or something like that. In fact, we theorize actually that we do not provide the proof of that for more complicated problems, the requirements for P will probably drop.
Okay.
Maybe Ruslan has some thoughts on this subject as well.
Well, I would just point out that these are numerical results.
Yeah, so these
take them as you will.
That's right. So these are heuristical results, empirical results. Yes.
Which are of course incredibly valuable because best classical algorithms are heuristics. So if we want to seriously compare classical algorithms with quantum algorithms, then we need to do numerical results. But this is not like a proof.
Right.
It's not the proof. And it is really hard to come up with such proof, right? Essentially, right, it's a battle of heuristics, right? When you change your problem, the question is going to be, first question you need to ask, how good is your classical solver, right? For this comparison to be meaningful. The reason why we chose max cut and the free regular graphs is because we know that the classical solver is actually kind of like, it's well known, it's like tested, right? And it's usually actually it's has one of the best solutions, implementations already existing.
Right. Thank you.
Hi, I'm an undergrad, so sorry if this question is coming out of left field, but I'm noticing a pattern in your talk where you are only dealing with some type of binary optimization problem where each individual state can only have 1 or 2 values because it's just binary in nature. But I'm wondering if you wanted to optimize a more complex type. I'm thinking that you would have to then somehow map it back to a binary optimization problem. So say you wanted to optimize like a float or something like that. You'd have to take that optimization problem and then map it down to a binary one. Am I correct in that thinking, or am I just coming out of nowhere?
No, that's completely correct. Yeah. So if you want to deal with floating point numbers, you have to deal with, same as in classical computers, you have to represent it. There is this floating point arithmetic. You encode your number in a certain way, and the same floating point arithmetic can be done on a quantum computer as well, assuming it's a fault-tolerant quantum computer, because that gets pretty complicated. Another way, if you have integers, so say your variable can be 1, 2, 3, 4, 5, and that's it. Then you can encode it in qubits. So not the 2-level qubit systems, but like in this case, 5-level system. And then you can also very naturally say that, for each variable, we have one qubit, and this qubit can be in one of the 5 states, and those are the 5 values of my integer variable. So that's another way to go about doing that.
Okay, gotcha. Thanks.
But you're completely on point.
Any other last minute questions? We're about to wrap up. All right. So, Ruslan, thank you very much. It was a great presentation. We really appreciate it. And so we are done for today, but tomorrow there is going to be, let me check out actually what's going to be tomorrow. So tomorrow we'll continue. We'll start again at 10 a.m. Central Time. And tomorrow is going to be, speaker is going to be Junior Liu from UC Chicago. And he will actually talk about quantum machine learning, how to basically implement these quantum algorithms, and also how we can solve the problems. So if you're interested in this subject, please join tomorrow. And that note, we are done for today. Sue, please stop recording.